long is a second? Put another way, how do you measure a second? For most of us, this question isn't a big deal. Maybe you've got a watch or a clock with a quartz crystal oscillator. These devices take advantage of the piezoelectric effect. Quartz turns vibration into electricity and electricity into vibration. In a quartz watch, a battery or other power source provides a little electric charge that goes into the quartz crystal, which vibrates at a specific oscillating frequency to shake off the built-up electric charge. In ideal conditions, that's measured at 32,768 oscillations per second. But we don't live in ideal conditions. Temperature changes the size of the crystal, which changes its frequency. The mechanical stress on the crystal will change as other parts of the clock shift around. The quartz may have tiny impurities that cause its frequency to deviate from that of pure silicon dioxide. The truth is, quartz can be synthesized pretty purely. It isn't that temperature sensitive or anything. And all in all, two quartz watches are going to be in sync at the end of the day. And sure, for most of us, quartz is a good enough oscillator. But that said, inaccuracies and instability in quartz are still noticeable. A few seconds in a month, maybe enough to adjust the minutes on the microwave clock a couple times a year. So now that we all have phones and computers of various sizes, we use a different system. Those devices typically sync the time over the internet using time servers, then maintain the time with their internal clocks powered by a little battery on the motherboard, which is what allows your computer to report the time quite accurately when you start it up, even if it isn't yet connected to the internet. Those time servers, in turn, broadcast the time from atomic clocks. They typically run on the Network Time Protocol, which broadcasts Coordinated Universal Time, abbreviated as UTC, because time is international and the acronym didn't match English. UTC is made up of a weighted average of 450 atomic clocks in about 80 national labs around the world. By averaging all these signals, they improve the signal-to-noise ratio and get substantially higher accuracy than any one clock in the system. And most of these atomic clocks are cesium clocks. These clocks use cesium-133, the only known isotope of cesium that's stable, that is, not subject to radioactive decay, but we can still induce tiny oscillations in its hyperfine structure in its ground state. The idea is that these oscillations arise from electromagnetic interactions of the atomic nucleus. Fine structure refers to shifts relating to electron spin, but cesium-133 also has this nuclear spin. When the atom is hit with radiation at an energy equal to the difference between these two little hyperfine levels, cesium-133 will absorb that photon, then, to return to a lower energy state, re-emit it with a wavelength in the microwave range. How long is a second? Well, the International System of Units defines the second as a unit of time in terms of cesium-133's oscillations in hyperfine state, such that 9,192,631,770 of those oscillations, at absolute zero, are equal to 1 second. And you might very reasonably ask, why not 9,192,631,771 oscillations? Mostly for backwards compatibility. We used to calculate the second as a fraction of the tropical solar year, which at least is a more stable period than the Earth's rotation, the day. This produced a second that was a fraction 1 over 31,556,925.974 of a tropical year. And for the record, I hate expressing a fraction that way, with a decimal in the denominator, but the other option is 12,960,276,813 over 408,986,496 times 10 to the negative ninth of a tropical year, etc., etc. The point is, the second, as defined by cesium clocks, is intended to match that cursed freaking number. And it's great. This kind of radiation in response to a specific amount of energy is incredibly stable and reproducible. There's no such thing as impurities in a cesium-133 atom. The frequency of its oscillations give it a high time resolution, 9.2 gigahertz versus the quartz's 32-ish kilohertz we talked about earlier. In fact, it's so good that, you know how I mentioned we used to define the second in terms of the year? Now we define the year in terms of the second. In the International System of Units, there are 7 defining constants, things like the speed of light or the elementary charge of a single proton. The second, as defined by cesium-133, is one of those constants. Base SI units are defined in terms of those constants. The meter is the distance traveled by light in a vacuum in 299,792,458 of a second. The kilogram? Also defined partly in terms of the second. The mole is the only base unit that isn't measured in terms of time, and only a handful of derived units do not depend on the second. So if you're getting the impression that our whole international measurement system depends on cesium-133, that's super fair. Yeah, that's pretty much what's up. But in the study we're going to talk about, our researchers are part of a movement to change that definition of a second. Why? Why would we mess with a good thing? Cesium is stable. Like, these clocks wouldn't gain or lose a second in 6 million years stable. It's reproducible. It's grounded in fundamental physics, and we're really good at measuring its oscillations. I mean, we could be more precise. And to me, cesium-133's 9.2 gigahertz frequency seems incredibly precise, but remember, that period corresponds to the microwave range of electromagnetic radiation. Microwaves are defined in the megahertz to mid-gigahertz range, like our cesium-133's radiation. What our researchers are testing are optical clocks, which work in the visible light range. Just like cesium-133 with its 9.2 gigahertz frequency has a higher time resolution than quartz with its 32-ish kilohertz frequency, an oscillator with an even higher frequency, like visible light, is capable of an even higher degree of precision. Now, cesium-133 can't be that. The period of its little hyperfine oscillations are determined by its properties as an atom. But, I mean, what if we apply atomic clock principles to a different atom, one with different properties that result in optical radiation? You know, light, rather than microwaves. Fortunately, there are like half a dozen candidates. You can see that cesium and other left side of the periodic table atoms work in microwave clocks, while atoms like aluminum, strontium, ytterbium, mercury, iodine have these little hyperfine ground state transitions in the optical range. Rubidium can apparently do both, as we see. Yet another reason it's the physics golden child of the periodic table. Finding an atom that can be used for an optical atomic clock was one thing, but the other challenge is the measurement. You do have to detect all these hyperfine transitions. Highly accurate detection was a bottleneck for optical clocks for a long time, but about 25 years ago, physicists cracked that code with something called a frequency comb, and as a result, we have optical clocks that are up to 100 times more accurate than the state-of-the-art cesium design, and they're just as, if not more, stable. That leaves us with a problem. We have clocks that are more precise than the units we use to define them. And no, that doesn't stop scientists from using optical clocks for their ultra-precise measurement. Physicists use optical rather than cesium clocks all the time. But the longer we have these optical clocks, the more it's like, well, shouldn't we change the standard unit to the most precise thing we have? Ideally, yes, and for what it's worth, the standard units people are super down for it. But to make such a big swing, we do need to experimentally confirm that we can use optical clocks in the kinds of ways we currently use cesium-based clocks. One of those is coordination. Remember that time on our phone is based on a weighted average of hundreds of mostly cesium-based atomic clocks at 80 different national labs? Well, optical clocks have mostly only been tested in pairwise comparisons. if optical clocks are going to be a time standard moving forward, we have to show that it's feasible to operate a network of optical clocks the way we currently do with cesium-based clocks. This paper in the latest issue of Optica coordinates between 10 clocks, making it the largest coordinated comparison of optical clocks to date. That right there should tell us how far we have to go with optical clocks. Using various atomic clocks, variations on strontium and ytterbium seem particularly popular, our researchers networked various atomic optical clocks. All of them were networked over satellite, and some subsets were linked optically. Unsurprisingly, the fiber link did not extend from Europe to the National Metrology Institute of Japan. From there, they compared these clocks as they ran for 45 days. Some of these comparison measurements had been made before, others are novel measurements. In previous studies, comparisons between multiple optical clocks had yielded unexpected discrepancies, and this study did find some inconsistencies as well, but even so, these comparisons ended up offering proof of concept supporting the idea that these clocks can be successfully networked, which may someday allow us to switch up how you get the time on your phone. But it's also the beginning of a longer campaign to determine which optical standard might be the best one on which to base the unit of the second. After all, you can make an optical clock out of plenty of things, but you can't define the second by all of the things. Previously, we picked cesium. If we do shift the definition of the second to a standard in optical frequencies, we're going to have to pick a favorite. Comparison studies like these help researchers identify the best candidates for a new definition of the second. No spoilers for that one, as these studies' authors insist more research is required. Reading it, it's kind of like leaving an enticing plot point to get the studio to renew your TV show for another season. Except with atomic clocks. Now, for most of us, a change in the definition of the second affects nothing. I'll probably never notice if they swap the coordinated universal time from cesium to, I don't know, single ion ytterbium. Heck, I still have plenty of quartz clocks around doing useful things in my day-to-day. Although the clock by my sink is constantly running slow, so maybe that one's not the most useful. But these kinds of hyper-precise measurements enabled by optical clocks allow us to do fundamental physics, and as we've talked about today, the science of measurement is a pretty cool science in its own right. So, how long is a second? We may have a better answer for you soon. Any second now.